Okay.
Do you want to use the collector?
Does it work?
We've got it here indicating that it's being recorded.
I see.
Click on it.
Okay, try it again.
Yeah.
Okay, that works.
Okay, great.
And so you can see this, and that's good. Can we move the bar out of the way? Oh, maybe it'll.
Yeah.
Yeah. Also,
Okay.
now we don't need this.
Okay.
Thank you.
Okay.
Thanks. So maybe let's wait for. Yeah.
Oh, a few minutes. Okay.
A few minutes. So you're also going to write something on the board.
Yeah, I was going to use like a
Okay.
step board.
So I'm going to open the line.
So it's
That's amazing.
the closest one. It turns on the blackboard one.
This one. Or... Okay. So how to turn on this light? Okay.
Yeah, I think isn't it the closest one?
Oh, this one.
Yeah.
Oh, I see. Okay. Thank you.
Can you see that? Is that good? Is it is better with or without the light? I don't know. I'm mostly going to be using the slides. Yeah. Okay.
Oops.
What happened?
Oh. Happened.
Just one thing I want to tell. Sometimes in this room, crazy things happen, and the screen turns off suddenly. So maybe this is one of these bad days. I want to warn you.
Okay.
No, maybe.
What did you do to get back on? Did you?
Just press. If you press black screen,
Oh.
then because if you press again,
Okay,
then
well-
go faster.
Okay.
Yeah, I do that if you.
No, I mean, I can do it.
So are you ready?
Yeah. There's the time? Yep, okay.
Yeah, it's time. So okay, welcome everyone. So today it's my pleasure to introduce Robert Young from New York University. He's going to give the colloquium. So Robert got his PhD in 2017 in University of Chicago.
2007.
2007. And Shmuel Weinberger. So he works on various aspects of geometry and topology, more specifically metric geometry, quantitative geometry, geometric group theory. And he has settled some major conjecture by Gromov on fitting function on arithmetic lattices, and he also does some very important work on like embeddings of Heisenberg group, which is what he's going to talk about, which actually has some important application to sparsity card problem in computer science. And he also give an ICM address this summer. Okay, let's please start.
Thanks. No, it's great to be here. This is some relationship to Sparse's cut, but I'm not going to talk about Sparse's cut here. If you're interested, feel free to ask. Okay, yeah, so what I want to talk about today is embeddings of the Heisenberg group into Banach spaces. Basically, the Heisenberg group is arguably the simplest non-commutative group. The Banach spaces are arguably, you know, the simplest abelian groups. And so what I wanted to talk about today is how that commutativity and non-commutativity affects the geometry. I kind of want to do three things. I want to introduce the Heisenberg group and the geometry of Banach spaces. I want to try to convince you that the non-commutativity of the Heisenberg group means that metric preserving embeddings of the Heisenberg group into Banach spaces have to be bumpy in a certain sense. And I want to try to convince you that the Heisenberg group embeds better into Banach spaces that allow for bumpier embeddings. So to start, let's talk about the Heisenberg group. Let me introduce the Heisenberg group. So the Heisenberg group is a three-dimensional nilpotent Lie group. You can write it as a group of 3 by 3 matrices like so, with ones along the diagonal, x, y, and z above the diagonal. And this group contains a lattice. If I set x, y, and z to be integers, then I get a lattice, the integer Heisenberg group, and that's finitely presented. It's got generators x, y, and z corresponding to the matrix where x is 1, y and z are 0, or where y is 1, x and z are 0, and so on. And you can calculate, you can do some matrix multiplication to calculate that the commutator of x and y is z, and the commutator of x and z and the commutator of y and z are both the identity. So this is the Heisenberg group, or at least this is the algebra defining the Heisenberg group. We want to think about it more geometrically. So how can we put a metric on this? Well, we can look at the Cayley graph of the Heisenberg group. So this is a picture of the Cayley graph of the Heisenberg group. The Cayley graph of a group has one vertex for every element of the group. So here, the elements of the group are integer points in R3. And two vertices are connected by an edge if you can get from one to the other by multiplying by one of the generators. And so you've got 3 generators, x, y, and z, corresponding to these 3 directions. If you multiply by x, it increases the x coordinate by 1. If you multiply by z, it increases the z coordinate by 1. If you multiply by y, it increases the y coordinate by 1, but it also adds x to the z coordinate. And so you see that in this picture because these lines are sloping more and more upward as you go from left to right. And if it continues this the other way, they'd start to slope downward. So you can see the relations that define the group in the Cayley graph. So in the presentation on the previous slide, I said that x commutes with z. That corresponds to the fact that if you multiply x, z, x inverse, z inverse, you get back to the identity. Likewise, y commutes with z. If you multiply y, z, y inverse, z inverse, you get back to the identity. And the commutator of x and y is equal to z. So if you go in the x direction, y, x inverse, y inverse, that corresponds to moving one step in the z direction, moving one step up. So the commutator of x and y is z. And you have bigger copies of this relation as well. So for instance, the commutator of x squared and y squared, if you do the matrix multiplication, x squared times y squared times x to the minus 2 times y to the minus 2 is z to the 4th. And more generally, x to the n times y to the n times x to the minus n times y to the minus n is z to the n squared. And these commutators, these sort of spiral paths in the graph, have a big influence on the geometry of the group in a couple of different ways. So one is that all these paths are actually scalings of the same path. If I take this 1 by 1 by 1 spiral and I stretch the x coordinate by a factor of 2, the y coordinate by a factor of 2, the z coordinate by a factor of 4, I get this bigger spiral. If I take the whole group and I stretch the x coordinate by a factor of 2, the y coordinate by a factor of 2, the z coordinate by a factor of 4, I get this denser lattice. And in general, I can replace x by x to the n, y by y to the n, z by z to the n squared, and get an automorphism of the group. The whole group has a scaling which acts by multiplying the x coordinate by n, the y coordinate by n, the z coordinate by n squared. Consequently, that gets to another aspect of these curves, which is that these are the most efficient ways to move vertically in the group. So you can see that each of these curves is an n by n spiral, so the path of length 4n in the graph that moves n squared distance vertically. So when n is large, n squared is going to be much larger than 4n. This is going to be a very efficient way of moving up and down in the group. And that has a big effect on the geometry. Well, partly one way because it has a big effect on what the geodesics look like. If I have a geodesic between 2 points in this graph, if I have a shortest path between 2 points in this graph, then that path has to be mostly made up of these red and blue lines. It can't contain very many vertical segments, because if I have a path that contains a lot of vertical segments, if I have a path that contains a long vertical stretch, then I can replace that with one of these spiral paths that I can make it a little bit shorter. So the number of vertical edges in a shortest path in this graph is bounded. It's okay so far? So this gives us, so this tells us about the geometry of this graph, of this discrete group. What about the Lie group as a whole? Can we get a metric on the Lie group as a whole? Well, one thing we can do is scaling, is to use the scaling one. Scalings of the lattice in this group are going to get denser and denser and denser. If I keep on repeating this scaling, or scaling by larger and larger factors, I'm going to get denser and denser lattices. Those lattices are going to converge to the whole group, and I can take the metric on those lattices and take a limit to get a metric on the whole group. What does that metric look like? Well, on one hand, we constructed that metric by taking a limit of scalings of this group. So we hope at least that this limit metric has the same scaling, has this n by n squared scaling. Two, we've seen that this spiral path, this path here lies in the group, and after the scaling, that path still lies in the group. So we should still see those spirals in the scaling limit, in the metric on the Lie group. In fact, what we get when we do this process, when we take a limit of scalings of these groups, what we get is a sub-Riemannian metric. It's something called a sub-Riemannian metric. A sub-Riemannian metric is like a Riemannian metric, except the lengths of some vectors can be infinite. Basically, at every point, you have a subspace of the tangent space on which the lengths of vectors are finite and given by a norm. And any vector that's not in that subspace has infinite length. So just like a Riemannian metric, you want to define the length of the distance between 2 points to be the length of the shortest curve between them. But the big difference now is that a curve is only going to have finite length if all its tangent vectors are in these horizontal planes. A curve is only going to be finite length if its derivative is finite length almost everywhere. So we call curves like that, where the tangent vectors lie in this distribution, we call those horizontal curves, and then we define the distance between 2 points to be the length of a horizontal curve from U to V. In particular, if I want to take 2 points that are separated vertically like this, I can't go straight up and down because that's a path of infinite length. Instead, I have to kind of go around in a circle. I have to go right so that the planes start to tilt. Then I can go along the plane to go up, and then back to the left, and then back to around to where I start. Basically, all of these planes are spanned by these red and blue edges, and so the shortest path from here to here ends up being a horizontal path like this. Ends up being a spiral kind of like this. Okay, so that's the metric. We wanted this to be scale invariant, and we have that. You can check that if you take this distribution of tangent planes and you stretch the x coordinate by t, the y coordinate by t, the z coordinate by t squared, it sends horizontal planes to horizontal planes, and it stretches each horizontal plane by a factor of t. So it expands distances by a factor of t. Consequently, that gives us a pretty good idea of what balls in this metric look like just by scaling, because, well, the unit ball around the identity. It's going to be some compact set. Maybe it's about 1 by 1 by 1. If I apply a scaling automorphism to that ball, if I scale that by a factor of epsilon, I should get a ball of radius epsilon. And that's going to stretch the x coordinate by epsilon, y coordinate by epsilon, z coordinate by epsilon squared. So the ball of radius epsilon is going to be roughly epsilon by epsilon by epsilon squared. Consequently, every vertical line in this picture has infinite length, but it also has Hausdorff dimension 2. If I want to cover this segment by balls of radius epsilon, I'm going to need about epsilon to the minus 2 such balls. And so this segment from here to here has Hausdorff dimension 2. As a consequence, this picture is not very geometrically accurate, because this picture draws all those vertical lines as sets with Hausdorff dimension 1. And if you had a really truly geometrically accurate picture of the Heisenberg group, all of these lines should have Hausdorff dimension 2. And so we can ask, okay, can we do that? Can we embed the Heisenberg group in Euclidean space, say, in a way that preserves the metric, in a way that, can we find, say, a bi-Lipschitz embedding from the Heisenberg group into R3? It turns out the answer is no. This is the theorem of Ponceau and Sims, that there's no bi-Lipschitz embedding of the Heisenberg group in Rn. And this follows from a theorem of Ponceau that every Lipschitz map from the Heisenberg group to Rn is what's called Ponceau differentiable almost everywhere. So what that means, when we say that a map is differentiable from Rm, when we say that a map from Rm to Rn is differentiable, what we mean is that if you look at sufficiently small balls in the domain, the map is close to linear on those balls, or it's close to affine on those balls. Ponceau differentiability is a way of adapting this notion to the Heisenberg the Heisenberg group and to nilpotent groups in general. A map from the Heisenberg group to Rn is Ponceau differentiable at a point if, when you look at sufficiently small balls around that point, the map is close to a homomorphism from the Heisenberg group to Rn. The reason that this implies that there's no bi-Lipschitz embedding is that because the Heisenberg group is non-commutative, you can't have an injective homomorphism from the Heisenberg group to Rn. It has to send the center, I have to send the commutator subgroup to 0. And so since there's no injective homomorphism, that means that on small scales, your map has to collapse the kernel of whatever homomorphism this is. Your map has to collapse the center of the Heisenberg group, has to collapse the vertical direction. So let me show you a little bit about how the proof of this works. Where is it? Can I write on this whole board without, and you can see it over there?
I can see.
Okay. Okay, so I'll use
First quarter of the middle board, the second board.
Okay, so you see a little bit of the second board. Okay, okay. So let me try to explain how to prove Ponceau's theorem, or sketch a proof of Ponceau's theorem. So the Heisenberg group. So here's the picture of the Cayley graph from before. The Heisenberg group is made up of, we can write it as either a union of these red lines going from side to side, or as a union of these blue lines going from front to back. So let's look at these red lines just to start with. Each of these red lines is isometrically embedded in the Heisenberg group. So that means that if I have a Lipschitz map from the Heisenberg group to Rn, and I look at restriction to one of these red lines, I'm going to get some Lipschitz curve, right? By Rademacher's theorem, that curve is differentiable almost everywhere, which is to say, I can find some small ball, a lot of small balls in this curve, a lot of small balls, where if I blow up in that small region, I get something that's very close to a line. Now, that's just one of these red curves. In fact, Rademacher is going to be true for all the restrictions to all of these curves. And with a little bit of measure theory, you can find a small ball where Rademacher's theorem holds for most of the lines through that small ball. You can find some small ball in the Heisenberg group. Here's our small ball, so that all the red lines going through that ball map to curves in Rn that are close to lines. And furthermore, because all these lines are close together, all their images have to be close together as well. They have to be going in roughly the same direction. So we can find some ball where all the red lines map to lines that are nearly parallel. Likewise, all the blue lines going through that ball in the Heisenberg group are going to map to lines in Rn that are nearly parallel. But then that causes a contradiction because, well, in the Heisenberg group, we have these spiral curves. If you go out along a red line, out along a blue line, back along a red line, back along a blue line, you end up far away from where you started. You end up at a different spot than where you started. But then the image of this spiral curve is going to be a curve that goes out along a red line, out along the blue line, back along the red line, back along the blue line, is going to be a curve that's nearly closed, that nearly closes up. And so if you find a ball like this, and Rademacher's theorem guarantees that you can find a ball like this, if you find a ball like this in the domain where all the red lines map to nearly parallel curves and all the blue lines map to nearly parallel curves, then vertical distances in that ball have to be collapsed by the map. The map can't be can't preserve the metric very well on that ball. So this is the idea of Ponceau's theorem. If your map is too smooth, then it collapses vertical distances. So, okay, well, we can't construct an embedding of the Heisenberg group into Rn. Maybe we can do something a little weaker. So we can ask a different question. How well can we embed pieces of the Heisenberg group into L2? Because, well, so for in particular, say we take the ball of radius r in the lattice. That contains finitely many points. It contains about r to the fourth many points. And any finite metric space you can embed in Rn with, you know, some by Lipschitz constant. Because it's a finite space. There's no issue with that. The question is, okay, how big is that by Lipschitz constant? How much distortion is there in this embedding of this finite metric space in Rn? And so Aswad proved a theorem that if you take the ball of radius r, actually, this is a very special case of Aswad's theorem. Aswad's theorem itself is a very general theorem about doubling metric spaces, but this is a very special case applied to the situation we're looking at here, which says that if you have the ball of radius r in the lattice, then there is a map f to L2, so that for any pair of points in the ball, the distance between f of x and f of y is at most the distance between x and y. So this is a distance decreasing map, but it's at least 1 over root log r times the distance between x and y. So it's a map that decreases the distance, it's a distance decreasing map that doesn't decrease distances too much. And this is the factor by which it can decrease distances. So if we have a map like this, we say this is a map that has distortion on the order of root log r. We can embed this discrete metric space into Rn with root log r distortion. Okay so far? So what does this map look like? How can we construct a map like this? Well, Ponceau's theorem, this argument from Ponceau's theorem, suggests that if we have a map like this, if we have a map that preserves distances fairly well, then it can't be too smooth. Because if your map is very smooth, it's gonna run into this problem. You're gonna be able to find some ball where lines in that ball map to nearly lines in Rn. To avoid that, you need some construction that makes a bumpy map. A map with root log r distortion has to send lines in the Heisenberg group to bumpy curves in L2. And what do I mean by bumpy? I mean curves that are not close to lines. So for instance, one way to construct curves like that is to do essentially the Weierstrass construction. We define a map f of x equals 1 over root k, and then times a point where the coordinates are, I guess, what do we have? So we have, in the first coordinate, you have a sine wave of amplitude 2 to the k and period 2 to the k. In the second coordinate, amplitude 2 to the k minus 1, period 2 to the k minus 1, so on and so forth. All of these coordinates are 1 Lipschitz. And so since we're in RK, we need to normalize by 1 over root k to make the whole thing 1 Lipschitz. And if we do that, we get a curve roughly like this. We get a curve which is bumpy at a lot of different scales. Because if you pick a point on this curve and you take a ball around that point, no matter what radius of ball you choose, you're going to see the oscillation in one of these coordinates. If you take a big ball, you might see the oscillation in the biggest coordinate. If you take a smaller ball, well, now you're looking at scales that are too small to see these waves with long periods, but you're at just the right scale to see one of the waves with a smaller period. So so we say that this is 1 over root k bumpy at k different scales, because if you take any ball of radius between 1 and 2 to the k, you're going to see one of these coordinates, and the magnitude of that coordinate is around 1 over root k. No matter what scale you take, and no matter what ball you take, this curve is going to be about distance 1 over root k away from being a straight line. Does this make sense? Is this okay so far? So how do we how do we use this for the Heisenberg group? Well, we try to do nearly the same thing. We define a bunch of coordinate maps, sigma I, that are each one Lipschitz, and so that sigma I oscillates with amplitude and wavelength both on the order of 2 to the I. The idea that they're kind of like this 2 to the I sine x over 2 to the I. And this is not too hard to do because of the scale invariance of the Heisenberg group. You just need to construct one of these maps, and then you can just rescale to get all the rest of them. So you construct use sigma sub I for scales from 1 to 2 to the k, and then you define a map f of x is 1 over root k times sigma kx, sigma k minus 1, down to sigma 0. And it turns out that if you do this right, this embeds the ball of radius r into L2 with distortion on the order of root log r. Basically because if you have 2 points where if you have 2 points in the ball of radius r, then the distance between them is at most r and at least 1, because these are points in the integer lattice. So the distance between them is between 1 and 2 to the r, which means that it's close to 2 to the I for some I between 0 and k. And so if you, so those 2 points are going to be well separated by one of these coordinates. And we have not so much control over what happens in the other coordinates, but we know that we know that they are decently well separated by one of these coordinates. So they're at least distance 1 over root k apart. On the other hand, all these coordinates are 1 Lipschitz, and so this whole map is 1 Lipschitz, and so they are at most, this is 1 apart. Okay, so far? And so you can ask, okay, well, can we do better than this? Can we embed the ball of radius, can we embed this space into L2 with smaller distortion than this? And it turns out the answer is no. There's a theorem of Austin, Noah, and Tessera that any embedding of the ball of radius r into L2 has at least on the order of root log r distortion. And the reason for this, well, one reason for this goes back to these bumpy curves. This is really the bumpiest curve that you can possibly draw, or at least, up to a constant, the bumpiest curve you can possibly draw, essentially because of the Pythagorean theorem. If you take a curve, if you take a line and you want to make it not a line, well, you can do this. You can perturb it by say this segment has length r. If we perturb by epsilon r to bring an epsilon away from a line, then that's going to increase the length according to the Pythagorean theorem. This is a right triangle, and each of these sides has length, what, 1/1/2 times 1 plus epsilon square, r over 2 times 1 plus root 1 plus epsilon square. But we know that that's approximately r over 2 times 1 plus 1/2 epsilon square. And so to perturb this line to be epsilon away from a line at 1 scale costs about epsilon squared length. The perturbed line, the original line segment has length r, the perturbed line segment has length about 1 plus epsilon over epsilon square r. And so doing that perturbation, adding a bump of scale epsilon, added a factor of epsilon squared to the length. And so that limits the number of scales that we can make it, that we can make this line bumpy. That means that this construction that gives us a curve that's 1 over root k bumpy at k different scales is really within a constant of optimal. And since our embedding of the Heisenberg group into L2 is made up of these bumpy curves, the limit on the distortion of embeddings into L2 is the same sort of Pythagorean theorem limit, that you can't make this map more than 1 over root k bumpy at k different scales. Is this okay so far? Are there any questions about anything so far? Yeah.
So in this case, your 1 over root k bumpy is just another name for this distortion constant?
When I say 1 over root k bumpy, I mean that that's at least that far away from any straight line. And for maps from the Heisenberg group to L2, the analog would be that in order to get a bumpy map, you need the map to be at least this far away from any homomorphism from the Heisenberg group into Rn. And but in order to make it bumpy, in order to push it away from a homomorphism, that means that the curves that make up the map have to be pushed away from straight lines. Yeah.
I take a look at the previous slide. It's like the definition of the distortion.
Oh, just so a map with distortion C is a map which is distance decreasing, but doesn't decrease distances by more than a factor of C.
So does it say anything about how you say the bumpy means that it's not going to be sigma alpha, just dipshits or
Well,
after you take an index.
well, yeah. So you would have to. So these are so in order to that. So in order to have distortion, and in order for it to have an inequality like this, your map has to be by Lipschitz. So you can't define a map like this on the whole Heisenberg group because there's no by Lipschitz map. So that's why I'm restricting to these balls in the integer Heisenberg in integer lattice so that I can deal with just a finite metric space.
So if we just think about B1 to L2,
Uh-huh.
are you saying, is that example that you're trying to say is that it's not going to be C2 or not even sigma alpha?
Well, it's hard to say exactly how you would construct. So like in order to make this work, you need to be away from a homomorphism at all scales between whatever the smallest scale in your domain is to whatever the biggest scale in your domain is. In the discrete lattice, in the ball of radius R, your smallest scale is the distance between 2 points, 2 adjacent points. Your largest scale is the diameter of the ball.
Oh, so you're saying that you cannot actually map a B1 to L2.
Yeah, you can't so the distort if you map B1 to L2, there's no by Lipschitz map. So any map, you can have that upper inequality, but that lower inequality isn't going to hold with any constant, any non-zero constant. And so the ball of radius 1 in the Lie group has infinite distortion.
We still have like bipolar.
Yeah, bipolar are easy, but by Lipschitz you can't. More questions? So yeah, and so like in particular, like if you let R go to infinity here and you take a limit, well, what's going to happen is that this square root is going to get bigger and bigger. Your limit is just going to collapse. Okay, so this is the best possible embedding into L2, basically because L2 satisfies the Pythagorean theorem. If I take a line segment, in order to perturb it to be epsilon away from a line segment, I need to add a factor of epsilon squared to the length. So you can ask, okay, what happens in Banach spaces that don't satisfy the Pythagorean theorem? So for instance, if I work in LP, if I have a segment of length 1 and I perturb it by epsilon to make it epsilon bumpy, then the length of the perturbed segment is going to be on the order of 1 plus epsilon to the p. And if p is bigger than 2, this is smaller, so we should expect to get bumpier maps. And in fact, that's what we get. If p is greater than 2, then we can construct bumpier maps. These are nearly the same as the previous construction. In each coordinate, it's going to be some function that oscillates with amplitude and wavelength on the order of 2 of the I. The main difference is that, well, each coordinate is 1 Lipschitz. We've got k coordinates, and we're working in LP. So in order to normalize so that the whole thing is 1 Lipschitz, we need to normalize by a factor of the pth root of k. And since that factor is going to be smaller than 1 over the square root of k, bigger than 1 over the, since the pth root of k is smaller than the square root of k, that means that we end up with smaller distortion. We end up with distortion only on the order of the pth root of log r rather than the square root of log r. And again, there's a theorem due to Lefort-Ganor that any embedding of the, this is essentially optimal, that any embedding of the ball of radius r into LP has at least this much distortion, has at least on the order of pth root of log r distortion. And so let me summarize. So if we're looking at maps from the ball of radius r into LP, then the distortion is on the order of the pth root of log r for p greater than or equal to 2. And so in particular, as p gets larger and larger, this distortion gets smaller and smaller. And this makes sense more or less because any metric space embeds isometrically in L infinity. So it's not unreasonable that as p gets bigger and bigger, as your space gets closer and closer to L infinity, the distortion of this embedding is going to get smaller and smaller. What happens on the other side of this graph? What happens when p is less than 1? Sorry, less than 2? Well, these maps that we've just been constructing are going to get more and more distorted. But it turns out that there are other maps that have root log r distortion. And the reason for this is basically that if you have any infinite dimensional Banach space, there's a theorem of Dvoretsky that this infinite dimensional Banach space almost contains a copy of L2. So you can never have distortion that's worse than the distortion that you get from embedding into L2, because you can always just take your metric space, embed it into one of these copies of L2 inside your infinite dimensional space, and then call that your embedding. So you can never get more than root log r distortion, even when p is smaller than 2. And so by the same theorem of Lefort-Ganor, this bound is sharp when p is greater than 1. And then that leaves one more point, which is what happens at exactly p equals 1. What happens for embeddings from the Heisenberg group into L1? It's a theorem, so the first bound in this direction was due to Tiger, Kleiner, and Knorr, who show that there is some power alpha, so that any embedding of the Heisenberg group into L1 has distortion at least on the order of log r to the alpha. But the alpha they got was a very small number, somewhere on the order of 2 to the minus 50. And then a couple of years ago, Asaf and I proved that in fact, you can find a sharp bound on distortion of embeddings of the ball of radius r into L1, but there's actually a discontinuity in this graph. The best embedding of the ball of radius r into L1 has distortion on the order of 4th root log r rather than square root log r. And so this is a neat result. Like one of the consequences of this result is the following theorem: that there's a metric space based on the Heisenberg group that embeds bi-Lipschitsly in L1 and L4, but not in any LP in between, which you get basically by taking the Heisenberg group, embedding it into L1 by this 4th root log r distortion map. It turns out that, well, so what does that mean? You take the Heisenberg group, you change the metric by a factor of 4th root log r so that it embeds bi-Lipschitsly in L1. It turns out that that change is enough to also get the Heisenberg group to embed bi-Lipschitsly in L4. But that change in the metric is not enough to embed bi-Lipschitsly in L2, because in order any embedding into L2 has to have distortion at least root log r, and this only has distortion in 4th root log r. So you can use this to construct a metric space, which is the Heisenberg group with a slight change to its metric that embeds bi-Lipschitsly in L1 and L4, but not in any of the LP spaces in between. Is this okay so far? Yeah.
So are you saying that the line between L and L2 is also sharp?
Yeah. So above for p greater than 1, this is a theorem of Lefort-Ganor that these are. I think Lefort-Ganor proved the upper bounds. Lefort-Ganor proved the lower bounds. Upper bounds follow from Aswad's theorem and Dvoretsky, I guess. More questions? Okay, so what happens then what happens then at t equals 1? How is the geometry of L1 so different from the geometry of these other LP spaces? So that's what I want to try to explain for the rest of the talk, which is, how long do I have? Okay. So yeah, so what happens in L1 that leads to this discontinuity? Well, the first thing that happens is that the argument that we made before about differentiability doesn't work in L1. Lipschitz maps to LP spaces for p bigger than 1 satisfy the Radon-Nikodym property. They have to be differentiable almost everywhere, but Lipschitz maps to L1 don't have to be differentiable anywhere. The standard example is this function. If we define a map f from the unit interval to L1 on the unit interval, which sends t to the characteristic function of the interval between 0 and t, then you can check that this is an isometric embedding. The distance between f of t and f of s is a norm of s minus t. But it can never be approximated by a linear map because, well, you know, at time t, at time t, you have a function that looks like this, and then at time t plus epsilon, you have a function that looks like this. Halfway in between, you know, the average of those two functions would be a function that has 2 steps like that. But in practice, your map at the midpoint, your map lands at that function. So this is a function which is an isometric embedding that can never be approximated by a linear map. In the terminology we were using before, this is a map that is, you know, 1 bumpy at every scale. It is never close to a linear map, and so that opens up a new collection of possible examples, a new way to construct embeddings of metric spaces into L1, which is to try to construct maps from, say, the Heisenberg group to L1, so that every point f of x is the characteristic function of some subset of the Heisenberg group, to try to generalize this construction to the Heisenberg group. Is this okay so far? So let's do this. Because the Heisenberg group is a group, it makes sense to try to make this as symmetric as possible. So what we're going to do is we're going to pick some set S, some subset of the Heisenberg group, and then we're going to define f sub s. So the f sub s of g is the characteristic function of some translate of s. The way I've set it up, the distance between fs of p and fs of q is going to be the difference between the characteristic functions of 2 of these translates. And you can calculate that this is the measure of the set of points in the Heisenberg group, so that exactly one of GP and GQ is in your set. This is, I think the easiest way to explain this is to go through an example. So let's take, say, our set to be the unit ball in the Heisenberg group. And then we want to know, if we have 2 points P and Q in the Heisenberg group, how far apart does f sub d take those points? So 1, if P and Q are very far apart, remember d is the ball of radius 1, d is the ball of radius 1. So if we have 2 points that are very far apart, much more than 1 apart, then any translate GP and GQ, one of them may land inside the ball, but you can't fit both of them inside the ball. And you can translate this segment so that P lands in the ball and Q lands outside. You can translate so that Q is in the ball and P is outside, but you can't translate so that they're both in the ball. And so what that means is that, well, the distance between f of FDP and FDQ is the number of translates where one lands inside the ball and one lands outside the ball, is the number of translates where P lands inside the ball plus the number of translates where Q lies inside the ball. So once these points are far enough apart, it doesn't matter exactly what their distance is. the distance between FDP and FDQ is going to be on the order of 1. If these points are closer together, say P and Q are close together along a horizontal line like so, then now if they're close together, now there are a lot of translates where they both land inside the ball, and a lot of translates where they both land outside the ball, and fewer translates where one of them lands inside and one of them lands outside. The translates where one of them lands inside and one of them lands outside are basically the ones that are around the edge of this ball. And you can calculate that the measure of those is basically, the perimeter of this ball times the distance between P and Q is roughly T times some constant. So if P and Q are close together along a horizontal line, then the distance between FDP and FDQ is on the order of T, the order of the distance between P and Q. So that's pretty good. I mean, this is if P and Q are close together along a horizontal line, then this map is preserving the distance between P and Q. The place where we run into problems is the same place that we ran into problems earlier. If we have 2 points P and Q that are close together along a vertical line, then, well, the translates that land one of them inside the ball and one of them outside the ball, by the same argument, they're going to be the translates that take this line segment so that it intersects the boundary of the ball. The number of translates like that depends on T. So the distance between f sub d of P and f sub d of Q is on the order of the vertical separation between those 2 points. But because of the metric on the Heisenberg group, the vertical separation between those 2 points is on the order of norm T. But the distance in the Heisenberg group between those 2 points is root norm T, because in order to get from one to the other, you have to take one of these spiral curves. And when T is small, norm T is much smaller than root norm T. And so this map preserves distances between horizontal, this map preserves the distances between horizontally separated points pretty well, but it's collapsing the distance between vertically separated points. It has the same problem as the previous maps that vertical line segments map too close together. Is this okay so far? Okay. So then we can ask, okay, how can we improve this? This embeds horizontal lines well, but it collapses vertical lines. How can we improve this? Well, we need to construct some set S that has more vertical perimeter. So that more of these translates of vertical segments cross the boundary of S. We need to construct some more complicated S. The problem is, if we do that, if we just construct some very complicated S, then on the one hand, we've kind of achieved what we wanted, in the sense that now there are more vertical line segments that intersect the boundary, and so vertically separated points are mapped to points that are further apart. But the problem is that now if we're not careful, there are also a lot more horizontal segments that intersect the boundary. And so horizontally separated points are also going to be mapped further apart. And that's not good, because we want this map to be distance decreasing. We want this map already separated horizontal lines pretty well. We don't need to increase if we have a lot more horizontal intersections like this, it's just going to cause more distortion. So what we really want to do is we want to construct some set S that intersects roughly the same number of horizontal line segments, but a lot more vertical line segments. Does that make sense? Is this okay so far? Are there any questions about any of this? Okay. So what can we do? Well, so we need a surface that cuts as many vertical lines and as few horizontal lines as possible. And so what we're going to do is we're going to start with a vertical plane, say this plane on the left, and then we're going to perturb that plane. We're just going to perturb it left and right, so it's still going to intersect the same number of horizontal lines as before, but those perturbations should be enough to intersect more, to cut more vertical lines. If this weren't the Heisenberg group, if it weren't for the non-commutativity, if all these red lines and all these blue lines and all these black lines were all parallel, there would be a nice way to do this where you just take your vertical plane and you just corrugate it. You add a, you add a corrugation. I can never draw this properly. I never know how to draw this properly. I usually just grab a sheet of paper. You take your vertical, you take your plane, and you do this to it, and those corrugations extend infinitely to the left and right. The trouble is that in the Heisenberg group, if you do that, if I take this plane and I add a corrugation to it, that's going to increase the x coordinate as part of my surface. That means that the lines in the y direction start to tilt as the x coordinate increases. They're going to go through that corrugation. So we can't, have corrugations that go infinitely, but what we can do is we can add bumps to this surface that are aligned along these blue lines. And adding those bumps is going to increase the number of vertical lines that get cut. It's going to increase the number of horizontal lines that get cut as well. But if we're careful, it shouldn't increase that number by too much. And in practice, what you get looks like this. So here's our, we're going to do this iteratively. We're going to add one set of bumps and another set and another set. So here is our first set of bumps. We started with a vertical plane, and then we added one bump just in the middle like that. The left and right are sort of 3D pictures, and the picture in the middle is shows how the horizontal planes intersect our surface. Remember, in the middle of the bump, x coordinates increased, so the horizontal lines have started to tilt, and you can see that here their slope is bigger in the center of this bump than on the sides. What does that do? So remember what our goal was. Our goal was to increase the number of vertical lines that get cut without increasing the number of horizontal lines too much. If we add a bump like this, that does what we want. It increases the vertical lines that get cut, but it doesn't increase the horizontal lines too much. But the problem is that the thing is that works well at one particular length scale. If I have, because really I have an infinite periodic surface. I have infinitely many bumps going all the way down. That increases the number of vertical segments of about this length that get cut. Because about this length, that's about half a period, and so it's pretty likely that one of those endpoints is going to be inside and the other one's going to be outside. But if I have lines that are much smaller than that, that's much smaller than a period. If I take a segment like this, it's probably entirely inside the picture or entirely outside the picture. And so this first step fixes the embedding at one particular length scale, roughly the distance from here to here. In order to fix the embedding at smaller length scales, we need to do the same thing again. We need to add another set of bumps at a smaller length scale. As we do this, because remember in the first stage, we started to tilt the horizontal planes. So our next set of bumps has to be aligned along those curves. They have to tilt more in the center than on the sides. You get something like this. That fixes the embedding at scales about this size. If you want a smaller scale, we have to do it again. We have to add another set of bumps that again is lined up along the horizontal curves. And so they again tilt a little bit more in the center than on the sides, and so on and so forth. And then the end result of this is a surface like this, where if you take a vertical line going up and down through this, it's very likely going to go in and out of these bumps many, many times. But if you take a horizontal curve, if you take a horizontal line, it's more likely to go along these bumps more likely to go along these bumps, and so it's less likely to intersect the surface very often. So if you do this carefully, you can show that adding a layer of bumps of depth epsilon adds roughly epsilon to the fourth to the perimeter. Basically because of this trick of trying to stretch the bump out as far as possible, so that the slope along the bump can be as gentle as possible. So if we want to fix all the scales between 1 and r, we need log r layers of bumps. Each of those layers of bumps is going to have depth on the order of log r to the -1/4, and so this gives us an embedding with distortion on the order of 4th root log r. So this is the upper bound on the distortion of the Heisenberg group into L1. Is this okay so far? Are there any questions about any of this so far? Okay. So there's also a lower bound. This 1/4, this log r to the 1/4 bound is sharp. The lower bound is much more difficult to prove because, well, for the upper bound, you just need to construct one map. For the lower bound, you have to show that no matter what map you take, it has at least this much distortion. I can give you a quick, well, I won't even give you a quick sketch, I'll show you a picture. But so this is up to a constant, the bumpiest possible surface in the Heisenberg group. Basically because if you have any other surface in the Heisenberg group, you can decompose it into bumps like this. First step is a theorem that I proved with this off, that if you have a subset of the Heisenberg group, then you can decompose it into sets where the boundary of each set has what's called a correlative decomposition that approximates the boundary by a union of what are called intrinsic Lipschitz graphs. I'm not going to define what an intrinsic Lipschitz graph is, but I will show you this picture of an intrinsic Lipschitz graph. So this is an intrinsic Lipschitz graph. What I want to show you about this is that, oh, good, okay. So if you imagine going from the top, so you can see that it's sort of craggy. It's sort of like a cliffside, like a sedimentary cliffside where you have all these layers deposited one on top of another. And so you can imagine that if you started at the top of the surface and you went down, you would be crossing across all of these peaks. You would encounter a whole bunch of these very sharp peaks. But on the other hand, if you go from one side to the other, you can go along these gentle slopes. You can you have these paths sort of along these ridges or along these valleys that are much smoother. And furthermore, the slope of those valleys, the direction of those valleys, depends on the x-coordinate. As the x-coordinate increases, these valleys are going to slope one way. As it decreases, they're going to slope the other way. So if you have an arbitrary surface, you can decompose it into pieces that look like this. And furthermore, Asaf and I showed that if you have a surface that looks like this, then you can actually decompose it into bumps. You can construct what we call a foliated corona decomposition into quadrilaterals on which the graph is nearly foliated by lines. Again, this is I don't want to define what this is, but the idea behind this is very similar to this construction of a very bumpy surface. That you want to be able to talk about bumps on the surface that are both aligned along the horizontal curves in that surface, and where the width of those bumps might be much larger than the height, where the aspect ratio of those bumps can vary. And so you can first decompose your arbitrary surface into intrinsic Lipschitz graphs, and then decompose those intrinsic Lipschitz graphs into bumps, and you can get a bound on how many bumps of how many different sizes you can have. That eventually leads to this lower bound, this 4th root log r lower bound on the distortion of embeddings into L1. What can we say about all of this? To sum up, maps from the Heisenberg group to L2 and to LP for p bigger than 1 are governed by how bumpy curves in LP can be. Maps from the Heisenberg group to L1 are governed by how bumpy surfaces in the Heisenberg group can be. And So we can ask, how bumpy are surfaces in other nilpotent groups? How bumpy are surfaces in other spaces? And what can we say about embeddings of other spaces into Banach spaces? Thank you.
So have you started investigating any other reasonable groups?
I have some speculation. So one thing I can say is that the reason that I'm interested in asking about this for other nilpotent groups. I mean, we have this graph here, which we have this discontinuity at p equals 1 for the three-dimensional Heisenberg group. There's a generalization of the three-dimensional Heisenberg group. There's a whole series of Heisenberg groups. There's a 2n plus 1 dimensional Heisenberg group, which is a group of n plus 1 by n plus 1 matrices. And when n is bigger than 1, so 5-dimensional, 7-dimensional, and up, this discontinuity doesn't happen. This discontinuity only happens for the 3-dimensional Heisenberg group. In the 5-dimensional Heisenberg group, the distortion is still root log r for in L1. And so there's clearly some dependence on what nilpotent group you're looking at, though we don't know what the dependence is.
Are you saying that the HN is bigger than 1, we know that how sharp it is?
Yeah, so we know that like this graph is sharp. The exponents in this graph are sharp. And then when n, the difference between n equals 1 and n bigger than 1 is that when n equals 1, graph looks like this. When n is bigger than 1, then the graph looks like this. There's no discontinuity.
So the domain of this LP doesn't matter.
I mean, you need to be like big enough. Like little LP is enough.
No, I mean the domain is still 1 dimensional, like 0, 1,
Yeah, so little LP would be enough. Any infinite, you know, yeah, LP of the interval is fine.
So do we know anything about ego?
Not that I know of. I mean, the reason, one of the reasons that I like the Heisenberg group here is that it's very symmetric. Like, so I've drawn it in a slightly asymmetric way. But if you fiddle around with this parameterization a bit, you can make it so that instead of so I drew it like this, where the horizontal planes tilt as with the x coordinate. You can also draw it sort of in a more symmetric way, where the horizontal planes tilt according to the distance from the origin, and then so you have these rotational symmetries as well that you don't have in the angle group, because the angle group is not very
I'm
symmetric.
not saying angle is like x1 is 2 is 4, x1 is 2 equals x 3, x1 is 3 equals x 4.
Yeah.
That like step.
Yeah, so I don't know. I mean, so I don't know what happens for other nilpotent groups. And it would be interesting to try. It would be interesting to try. Okay.
We're also going to plan a dinner with this week at 6 p.m. It was the joint.
Well,
So I should close the stop sharing. Yeah, I'm going to send the link to Tracy.
And then
Yeah.
I just take this.
Okay. Yeah, please.
Just out of curiosity, does this have any effects for the concentration theory?
I don't know. Well,